All right, this is the Module 6B. I picked 3 problems similar to some of the ones in the homework to go through with you on this. So we're looking at Markov chains in this section, and we're talking about something where we're looking at the probabilities of having a change from one stage to another, or one status, I should say. So like from being in set A to changing to set B, or staying in set A or changing to set C. So all of these this is a transition diagram kind of here in the picture. Those are probabilities of, as we move from one stage to the next in this chain of processes, what's the probability that we will either stay the same set or move to a different set. You also usually have an initial distribution for your first stage. This is kind of, we call it stage sub-zero. So this is the initial stage where it says, and this is in the order usually alphabetically, or they'll have to tell you, but this is A, B, and C. So we start off with 50% of our items or objects or whatever it is we're counting. We've got a 50% chance that we're in set A, 20% chance in set B, and 30% chance in set C. So to figure out, using the transition diagram to figure out how we go to stage 1 and then stage 2 using this initial state matrix right here, we need to first set up our transition matrix. Okay, so I'm going to get my pen and let's talk about what that looks like. So we usually call that P, and I'm going to make a note kind of like the textbook does. This is usually from our current, so this little A, B, and C, this is the stage we're currently in, and then this is going to be where we're going on top, so A, B, C, so this is moving to the next. So that helps you follow the chain of the arrow directions. So this is a 3x3 matrix because there's 3 states and 3 possible directions for each one. So from A to A, it looks like is a 0.2. From A to B is 0.3. And from A to C is 0.5. A couple things to note when you're doing these, not only the transition matrix, but the state matrix as well, they always have a row that adds to 1. 100% of our items or elements have to be utilized in every state that we're in. So notice this adds to 1. So if you're ever missing one of these arrows, like they have a question mark on it, sometimes I saw that in some of the textbook questions, you can figure it out by making sure that the row adds to 1. That's not necessarily true for the column, but it is true for the row, okay? And then for B, from B to A is 0.1. From B to B is 0.8. From B to C is 0.1. From C to A is 0.4. From C to B is on the green line here, so 0.2. And from C to C itself is 0.4. So this is called the transition matrix. This is the transition diagram, the picture that they gave us. Okay, this is from just the properties in our book, and kind of how do you move with Markov chains from one state to the next. So going from our initial state to state 1, you have to take the state you're in and multiply it by the transition matrix, okay? So that's multiplying it by those probabilities of change. So for us, that is 0.5, 0.2, 0.3. That point a little bolder. And then we've got our transition matrix. 0.2, 0.3, 0.5, 0.1, 0.8, 0.1, 0.4, 0.2, 0.4. Now it's helpful if you use your calculator, obviously, to do these multiplication steps. That'll go a lot quicker. But I like to go through the ones I do on the video, just maybe one line where I remind you of kind of how we find it. I think those things are good, not to always rely on the calculator. Make sure you know what's happening, but also to know what your final answer is going to be. So this is a 1 row by 3 column. This is 3 row by 3 columns. So our answer, remember the middles have to match to be able to multiply. Our answer is still going to be a 1 by 3, the outer numbers, which makes sense because that tells us 1 row with 3 different sets. So that's going to tell us the probabilities now that we have however many elements, what percentage of them essentially is in each of those sets after we've done one transition. So to remind you, just to kind of, I'm going to do one note here and then I'll do the rest just using the calculator. You're doing row by column. So it's 0.5 times 0.2 plus 0.2 times 0.1, and then 0.3 times 0.4. So row by column and element by element. So this is what, 10, 0.10, 0.02, and 0.12. So that's going to add up to 0.24. Make sure I can write that nicely. I'll give it just a second. Pen's not wanting to register. There we go. So 0.24. And then I will go ahead and just give you the other answers. It's going to end up being a 0.37 for the next one. That's row 1 here by column 2. And then again, you would know, if you remember that I said the row adds to 1, that you can find this one without doing any matrix multiplication because it's the last item in this row. So this has to add up to 1, so that's going to have to make that 0.39. So that is our stage 1, or state 1 after the initial matrix has had a transformation using the transition. So again, this is really just matrix multiplication, but you have to kind of understand that if someone asked you about this, this would now mean 24% is in set A, 37% in set B, and 39% in set C. So let's do the last piece of this one, which is we want stage 2. That means you do stage 1, your previous answer you just got, times the transition matrix. So we had a 0.24, a 0.37, 0.39 times the 0.2, 0.3, 0.5, 0.1, 0.8, 0.1, 0.4, 0.2, 0.4. Okay. And I've already worked this out on my calculator. This is 0.241 for the first one, so row 1 by column 1, 0.446 for the second one. And again, if you add those together and subtract from 1, you get 0.313, which is also row 1 times column 3. And this is state 2. So now we're looking at about 24.1% in set A, 44.6% in set B, and 31.3% in set C. And that is all that we needed to do for number 1 here. Okay, so let's talk about number 2. It says, given the transition matrix P and the initial state matrix S sub 0, find P to the 4th and use it to find S to the 4th. Now, in your textbook, and what you'll notice is that here we're doing it one stage at a time. In this previous one, we were taking S sub 0 and moving it to S1, and then S1 and moving it to S2. And what you find is that another way of thinking about these is that you're just really applying the transition matrix multiple times, because we're just applying it, we're kind of like multiplying in order from left to right. So another way of thinking about finding S4 is to take your S sub 0 and multiply it by P to the 4th, because you're really doing that multiplying by the transition matrix 4 different times. So that's where we get that. So the question is, and you can use your calculator to figure this out. If you store this as a matrix in your calculator and you raise it to the 4th power, you should be able to get that answer pretty quickly. I'll show you another way of thinking about it if you want to do it by hand, especially since on your test, the only way I can really give you any partial credit if your calculator gets something wrong, which your calculator does what you tell it to, so it's only going to give you what you tell it to do, is to show some scratch work. So even if you use your calculator to do these calculations, this is really to save you with that partial credit component. So if you multiply the matrix times itself, the transition matrix, that gives you P squared. So I did that first, and that's on my calculator, I got 0.55 for the first entry right here. That was row 1 times column 1. But then that automatically tells me, since this is 2 by 2 and 2 by 2, this is also 2 by 2. So this is going to be 0.45, because the row has to add to 1. And then if I do row 2 by column 1, I'm going to get 0.30, which means this has to add to 1, and that's 0.70. So a nice little trick there. And then P to the 4th would just be P squared times itself, because remember, P times P, you add the exponents because they're same base. So this is 0.55, 0.45, 0.30, 0.70 times 0.55, 0.45, 0.30, 0.70. Now this one might be a little bit more lengthy if you wanted to show all your steps, but again, you can use the calculator. This, just seeing something written on your paper that shows me how you come up with your answers, is really the helpful piece when I'm giving partial credit. So then when I do row 1 times column 1, I get 0.4375, which means if I subtract from 1, I get 0.5625 as the second part of that row. And then row 2 times column 1 will give me the first entry down here, which is 0.375. And then subtract from 1, and I get 0.625. Okay, because these are probabilities, the rows have to add up to 1. All right, and then that's just getting P4. So we found P4. Now we want to find S4. So S4 is the initial matrix, which is 0.8 and 0.2 times this P to the 4th that we just found. 0.4375, 0.5625, that's row 1, and then 0.375 and 0.625. Okay, so we're doing row 1 times column 1. And that's the nice thing about this, is that really, because this is a 1 by 2 and this is a 2 by 2, we're going to get a 1 by 2 for our answer. It's going to match this same state setup. So I get 0.425 for doing row 1 times column 1, and there's the only other one entry here, so it has to add to 1, so 0.575. So this right here is S sub 4. Remember, this was P to the 4th. Okay, so nothing too horrible. Now this last one, I'm going to have quite a few things going on. We're going to come up with the transition diagram ourselves and then write the transition matrix once we have that. Then we're going to talk about how it is a regular Markov chain matrices, which means that for some P to the power, you have all non-zero entries. Anytime that occurs, so even if it takes you to P to the 5th to get to that point, then that would be what we call a matrix that has a long-term or long steady state behavior. And we're going to be able to find that stationary matrix. It means at some point, our states will approach the same thing no matter how many times we multiply it by the transition matrix. Essentially, you get steady stated or stationary. Okay, so that's kind of a three-parter. So there's a lot going on in this one. So it says a red urn contains 2 red marbles and 3 blue marbles. And a blue urn contains 1 red marble and 4 blue marbles. A marble is selected from an urn. The color is noted, so I guess they write it down. And the marble is returned to the urn from which it was drawn. So it's always going back with replacement to its original urn. The next marble will be drawn from the urn whose color was the same as the marble just drawn. So what that means is, if I grab from the red urn first and I got a blue marble, my next turn I will go to the blue urn, because the blue marble tells me to choose blue urn next. Okay, this is a Markov process with 2 states. You're either going to be choosing to draw from red urn or draw from blue urn. Okay, so we have 2 states. That means we're going to have 2 circles, and I'm going to color code them to help us see this. So this is our red urn. Over here, we have our blue one. Okay. Now, the probability, so I'm going to do kind of a, we'll do kind of a purpley. We'll do the orange color for the red. Now, what's the probability if I reach into the red urn, I'm going to then reach into the red urn again on my next turn? That depends on what are your chances of getting a red marble out of the red urn. So there's 5 marbles in the red urn and only 2 of them are red. So there's a 2 out of 5 chance, which we'll want to turn into a decimal for ease here, which is 0.4. So there's a 40% chance that if I reach into the red urn first, I'm going to reach into the red urn for the next state as well. Now, there's also a chance I'm going to have to move over and choose from the blue urn next. There are 3 out of 5 blue marbles in the red urn, which is 0.6. Okay. From the blue urn, if I reach into the blue urn, my chances of going back and reaching into the blue urn again has to do with how many blue marbles are in that urn. And that is 4 out of 5 or 0.8. So there's a high chance I'm going to reach back into blue again. And then the chance that I'm going to have be in the blue urn and then choose red urn next. Well, there's only 1 red marble in that urn. So that's going to be a 0.2. Okay, so that's my transition diagram. It tells me the probabilities that I'm going to move either to the same urn that I'm already in or to the other color. And that's purely based off of those choices that were within each urn because we were using the color we drew as our direction for the next state. Okay, so the transition matrix for this, P equals, remember this is going to be current to next. So I'm going to call it R and B for red and blue, and red and blue. So if I'm in red and a chance I'm going to get red again was 0.4. If I'm in red and I'm going to move to blue, that chance was 0.6. If I'm in blue, the chances that I'm going to move to red were 0.2. And if I'm starting in blue, the chance I'm going to stay in blue is 0.8. Okay, so we have our transition diagram, we have our transition matrix. Now we want to find our steady state or stationary matrix. And the reason we're allowed to do that is because this is a regular Markov chain. It's a matrices where there's a P to some power. And again, if there was a 0 in one of these, you would have to keep multiplying P times itself to first of all see if it ever gets to a place where it has all non-zero entries, because that's the only way we can guarantee that we have a stationary matrix. And since this is already all non-zero, we're able to do that, okay? So now we're going to actually find that stationary matrix, and then we're going to describe what that means for us as a sentence. So when you're trying to find the steady state, what you're doing is you're saying there's going to approach a point where I have two values for my state, since this is just two choices, two processes. And if I multiply that by P, which is 0.4, 0.6, 0.2, and 0.8, at some point along my journey, a stage multiplied times the transition matrix gives us back the exact same stage. So we are essentially stationary at that point for our stage, like say 5 to stage 6, it didn't change at all. So wherever that happens, that's what this is solving, this equation setup that we're doing. So we're trying to figure out what is the approaching probabilities or percentages, because a lot of times we'll write them as percentages, that we're going to be in either red or blue. So I'm going to write in here, red and blue correspond to these. Now, obviously we use kind of S1 and S2 as generic variables here, but they have to do with whatever our pieces up here are. They're still going to be red and blue just like they were before. So what this does for us, if these are variables, if we multiply this out and set it equal to the correct element or entry in the other side, we're going to get some equations. So row 1 times column 1 would be 0.4 S1 plus 0.2 S2 equals the first entry on that side. We also can get row 1 times column 2, so 0.6 S1 plus 0.8 S2 equals entry S2. If you just try to solve these two equations, you're never going to get anywhere, because these are actually going to be, if you set them like as a system of equations with, elimination or substitution, you're going to get an answer you can't solve for, because they're all going to cancel everything out. So here's the deal with this. You must also introduce another equation that we've talked about quite a bit, but it's always the one piece that people seem to forget when they're doing steady state or stationary, because a lot of textbooks will call it steady state. And that's the fact that anytime you have a row in a Markov chain, it has to add to 1. Those probabilities add up to 1, okay? 100% of whatever was going on has now been accomplished, okay? Here's the deal. You only need 2 of these to find the answers. And one of them has to be the S1 plus S2 equals 1. Now, obviously, if this was 3 variables and it was a 3 by 3 matrix, that's a little more complicated. You're going to have to be solving for 3 variables. You might have to use and you'll usually have 3 equations you get just from multiplying all this out. So you would have to use usually 2 of them and this one to find all the solutions. You have to do a little bit more work. But if it's 2 variables, you only need one of the ones you got from the equation setup and the fact that the row has to add up to 1. Now to use these, I'm going to do elimination by addition since it's just very basic here, but you need to get all of this to one side so it's all lined up. So we're going to subtract over a 1 S1 over here. And that reason I write this like this is so you can see that this is a -1 and a 0.4. So that's a -0.6 S1 plus 0.2 S2 equals 0. So I'm going to actually write that over here underneath this one. Now that I have it solved in a traditional general format. And then it's really easy to get rid of S1 if we just multiply the top equation by 0.6. So 0.6 S1 plus 0.6 S2. Don't forget to multiply 1 by this. That's going to be 0.6. Negative 0.6 S1 plus 0.2 S2 equals 0. That cancels. That's 0.8 S2. If I add the column, equals 0.6. And if I divide 0.6 by 0.8, I get 0.75. Now, essentially, if you're doing a 2-variable problem, we're pretty much done. The stationary matrix is going to end up being 0.75 for the S2 entry, and this has to add to 1, so it's 0.25. So there's my stationary matrix, okay? Now, if it was a 3-variable, again, more complicated, but the gist is the same. You set up all the equations by multiplying this setup together and getting all of those. You have to remember that all the variables in a row add to 1, and then you're solving using all of the different ways we've learned how to solve systems of equations. Now, there's one more piece to this, and I'm going to type it instead of trying to write it out. Maybe not. Let's see. Okay, so we want to talk about what does this mean? Well, in the long run, because that's what we're saying, it's long run behavior is what this stationary matrix is. 25% of our draws will be from the red urn, and 75% of the draws will be from the blue urn, because remember blue was the second position. So let's make that nice, line up with everything else. Oops. I want to put this somewhere else, so hang on. It's kind of gotten stuck with all of my other stuff. Let's just put it right here above it. There we go. So that is how you find the stationary matrix. That is kind of the sentence that you would write after finding it. You have to kind of tell us what percentage would be from each of those states. Essentially, we kind of get fixated at those percentages when we have this stationary matrix. So hopefully this was helpful and finishing up your 6B homework. And I look forward to any questions you have.